Thank you. Thank you to all of you for being so brave to be here last morning of this intense conference. And yesterday, after the first part, and after speaking to some people, I realized that I made some mistakes. So, for instance, when I wanted to speak about the separation of the roots, it was completely wrong what I wrote. So, anyway, it's not a big deal. It's correct in the notes. So, second thing, just because of some questions I had, when I said that my polynomials f1, fs define a zero-dimensional variety, I never assume that the polynomials, any condition on the polynomials, except that they define a zero-dimensional variety. So they are not a radical ideal until now. Okay, now I will resume with the shape lemma, and for the shape lemma, I assume that my polynomials f1, fs have coefficients in z, in the integer, over the integers, and they define a radical zero-dimensional ideal. Okay, radical, only simple zeros. And in that case, I think I said it yesterday, in that case, the dimension as a vector space, as a Q vector space of the quotient ring equals the number of points in the variety. So equal a number that I will call D. So remember that yesterday I told you that the good thing about zero-dimensional ideals or finite varieties is that they behave somehow, a zero-dimensional radical ideal behave as a univariate ideal. So that is what is called the shape lemma. It has lots of names. Shape lemma, univariate, rational univariate representation, geometric resolution, Kronecker parameterization, depending on when you find it. So that was already introduced in the late 18-something by Kronecker, and then it was reintroduced in the setting of computer algebra by many authors. So the first part of the statement I will show now is kind of classic nowadays. I am adding a part of the heights. I recall height. The height of a polynomial, of an integer polynomial, is the max, the log of the max of the absolute values of the coefficients, which is essentially the same than the bit size of the coefficients, okay? And for other works on the height of the shape lemma, there are also many people here in the room who did that. So maybe many. Here, Mohab, I forgot, Joris, Bernard, many people. So I will refer to, no, this is not the one, this is the one. So the version I'm giving is the version that we did in a recent paper with Bernard and with Lorenzo Baldi. And the setting, we have a radical zero-dimensional ideal. My polynomials belong to, have integer coefficients. The degree of the variety is called D. The deg of each polynomial fj is dj. As we had yesterday, they are ordered from bigger to lower, except for one polynomial that we can choose. One distinguished polynomial, fs, with its own degree and its own height. And the other polynomials have all height bounded by h. So first, the theoretical part, which has nothing to do with this. This is the shape lemma viewed as an isomorphism of quotient rings. And actually, it's very interesting, and let me explain. For those of you who don't know how it works, let me explain a little bit the proof of this. So are we going to show a symbolic shape lemma? So the idea is the following. Remember our friend, the Chow form of our variety. So the remember that I said that the Chow form was a polynomial in, here I will call u the variables a1 to an, and the Chow form was equal to the product for the zeros in the variety of the linear forms u0 plus u1 zeta 1 plus un zeta n that I will call L of u zeta. So I will have a generic linear form which will be u1 x1 plus un xn. This is a generic linear form with generic coefficients, variables. And then this was the Chow form. And for those of you who know about resultants, when your ideal is described by n polynomials, you can use the u resultant to compute this Chow form. But this is a property of varieties. So this was my Chow form yesterday. It was a polynomial. I put some coefficient here to make it belong to z of u, 0 u. And now I will consider these things. Instead of considering this polynomial, where is the eraser here? Here. I will put here a variable t, and here I will take minus u. So look what happens here. I have this polynomial. And this polynomial, what it happens is that every time I evaluate it in L of u zeta, for some zeta, what happens? If I evaluate it on L of u zeta, it vanishes, right? It's a zero polynomial. It's a polynomial in u, but it's zero, right? So all its derivatives are zero. And this is a composition of maps. It's composing the polynomial Chow v of tu with this L of u zeta minus. So when I take the derivative with respect to any ui, it's zero. So let me take the derivative. It's chain rule. For me, it's impossible to do a chain rule in the blackboard, so I will copy my formula. So I take the derivative of, with respect to ui of this map, and it gives the derivative with respect to the first variable, t, times the Chow v in tu of this map, evaluated in L of u minus u, times the derivative of this evaluated in zeta I in ui. So here I have a zeta I minus the part which corresponds to the ui. And this minus appears because I have this minus here. So these are many variables, right? So look at this. This is zero. As a polynomial, in u, it's zero. Which means that when I evaluate it in any value here for small u, it's zero, right? So let me choose a small u in z to the n such that the linear form L of this small u, which is defined as, here I forgot the x, L of ux, this is a concrete linear form in z of x, right? So when I evaluate this expression in this u, it's 0. So let me take a linear form such that it separates all the roots of v, in v. So here I have like zeta and psi, different. So for any zeta different than psi in v, let me take a linear form which does that. So I said that this polynomial is 0 when I put here my small u. What did I do here? I forgot a zeta, sorry. This is 0, right? What? Here, small l of zeta, sorry. L of zeta, like this. And here too, right? What did I do? Sorry. Thank you. Yes, sorry for that. Okay, so this is 0. This is 0, which means that this polynomial, here, remember that this is the variable t here. This is the variable t. So, which means that, and where can I write this? Which means that the polynomial, okay, I will write it like this. This polynomial, which is a polynomial now in t, this polynomial, which is a polynomial in t, when evaluated in L of, did you say zeta, is 0 for every zeta in V, right? I have a univariate polynomial in T, which is 0 on any L of zeta, where L is my linear form. But all these are different between them. So this polynomial is a polynomial of degree d, because the Chow form has degree d, which has d different roots. This polynomial has d different roots. And what happens with these roots? So imagine this, I will call this omega 0 prime. So, okay. So I will call omega 0, and let me get back to my notes, because if not, is the polynomial Chow v in t evaluated minus u, which is a polynomial in z of t. And the I will take these derivatives. Right? So what happens now when I can rewrite all this, and what I'm saying is that the derivative of omega 0 in times in times ci zeta I minus omega I evaluated in L of zeta is 0 for every zeta, which means that zeta I equals right? This is 0, so I just, and this makes sense because omega 0 is a square-free polynomial. I can derivate it and put it in the denominator. So look, this polynomial, this is true for any zeta in my variety, but I is a zero-dimensional radical ideal. So if two polynomials, omega 0 is square-free. So here I have the polynomial. This polynomial, sorry, I have to go to the other, I'm lost now, sorry for that. Okay, I'm lost. Here, big property. This is the important property we have for every zeta in V. And this is the core of the shape lemma. Are you following me? Because it's kind of hard. I knew it was harder today. So this is happening for every zeta in V. So look, let's define how I called it phi like this. From Q of X without, I don't take the I here. Here, I will define the following map of algebras. So the variable xi, I send it to omega I of t divided by omega prima 0 of t mod omega 0. So since omega 0 is a polynomial of degree d, this makes sense. I can invert this because omega 0 is square free. I can invert it and I take it mod omega 0. So I take this map. This is a map, well-defined map of algebras. And what happens is that because of this property, and because omega 0 is square free, and because I is radical, and using the Nullstellensatz again and again, what happens is that this map is surjective because phi of L of x, one can check easily that phi of my linear form is equal to t. So the map is surjective. And its kernel is exactly I, the ideal I. And to prove this, we strongly use the Nullstellensatz. We strongly use that I is a radical ideal. So why? Because these two polynomials coincide in all the roots, and here too. So it's just looking at the property and using the Nullstellensatz. So this shows that the map phi factors well to the quotient, like this, because of the theorem of isomorphism. So here we have this map that we were looking for, and it satisfies. So the first property is what I already showed. What is here? So now I show the existence of this omega 0, which is related to the Chow form, and of course the degree of omega 0 is equal to d because it has exactly d this different. It's defined. Thanks to the Chow form. The degree of the omega i's is bounded by d because of this, because we are taking mod omega 0. And what about the height? How can we derive this bound for the height? So remember that when I defined the Chow form, the height of the variety, it was using the Chow form. And there was this property that we never used before, which related the height of the variety with the height of the Chow form polynomial, the polynomial Chow form. So we had this property, which was this property. So here is the height of the variety, which was defined through the Chow form, but not as the height of the Chow form, something different with an alternative Mahler measure that I didn't introduce. But we had this inequality. And thanks to this inequality, I can, and because omega I and omega 0 and omega I are defined through the Chow form evaluated in t minus u, I can derive this height bound. So I left the height bound here in terms of the degree of the variety. I didn't replace capital D by the Bézout bound. Here the Bézout bound would be ds times the d1 to dn minus 1, for instance, but I left it in terms of the degree because I'm going to apply it to something where I know in advance the degree of the variety and it doesn't depend of the polynomial I'm choosing. So that's why I left it in terms of the degrees, but we could replace this capital D by the Bézout bound if we want. So why am I insisting on this? Because this is useful. So we have this relationship between our quotient ring, many variables, and the univariate ring. And this is useful, for instance, to derive height bounds for the remainder of any polynomial mod I. So imagine, now, remember that Q of x divided I is a d-dimensional vector space, and I can take for it a monomial basis. So I choose a monomial basis, simple one. It has dimension d. So I start with 1, then x1. If it's Li with respect to 1, I put it, and I just add monomials, and I will get a monomial basis and this monomial basis will have a max degree. The max degree of the monomial basis is what I will call the degree of B. And this max degree will be always bounded by the number of zeros, because we are adding until d things. So we have that. And any polynomial p in Q of x, I can write it as a sum of the generators of my ideal I plus a remainder. The remainder will be written in terms of the basis. And there is a unique way of writing this. And using this shape lemma, what we can do is bound. So the degree of this, we know it, because this remainder, it's like in the univariate case. The remainder will be written as a linear combination of the elements of the basis, right? Everybody can see here? So the good thing is that using that, we can bound with a better bound the height of the coefficients. So actually, when p belongs to z of x, this remainder won't need to stay in z of x. It might have rational coefficients. Because I'm dividing my polynomials in z of x, I can have rational coefficients, not non-integer, rational. But I will write it, this p, as a numerator times a denominator. So with np in z of x and a in z minus 0. Okay, so my remainder, I write it as an integer polynomial divided some common denominator. So what I will do using this shape lemma, I will be able to bound the coefficients of this integer polynomial numerator and the bit size of this a. Okay, better than if one just try to solve this as a linear system of equations. Even if we have a Gruber basis or whatever, the bounds we can obtain doing this are better than performing linear algebra. So this is what I show, I think, in the next slide, or not, or yes? Yes, this is what I show in the next slide. So doing that, that's the explanation, the remainder p. So we obtain the remainder p as a numerator divided by a common denominator, a number, with heights. They look ugly, but they are not so ugly. They are not, so they really look ugly, but they are not so ugly. And the thing here is, so the dependence here is on the height of p, the degree of p. D will be a bound for all the polynomials in the basis, for the degrees of all the polynomials in the basis of I. H will be an upper bound for the height of all the polynomials in I. And then P will have its own height and its own degree. And delta is the degree in the basis. Okay? So how do we do that? Using the shape lemma. So what we do is that using this isomorphism we had with the shape lemma, we can create a kind of univariate map from Q of x to Q of t over omega 0, which of course is isomorphic to 1 t d minus 1. So every polynomial here has an expression here. And this is a linear map. And the linear map will be defined thanks to this phi we had before. Any polynomial p will be sent to omega 0 prime times phi of p mod omega 0. So what is kind of immediate is that this map is surjective and its kernel is equal to I, which means that u of p is equal to u of the remainder of p mod I, because the kernel is exactly I. And the good thing is that we can bound the size of this u of p. So u of p will be a rational polynomial. If p is a rational polynomial, u of p will be a rational polynomial. But a rational polynomial of degree at most d minus 1 with some coefficients. So using the shape lemma, we can bound the size of a numerator and the denominator for u of p, simply because if we consider the ideal j equal f1, fs, and xn plus 1 minus of x. This ideal is an ideal with one more variable. I add a variable, but because f1, fs is zero-dimensional, this ideal is also zero-dimensional because its roots are simply the zetas I had before and then p of zeta as a last coordinate. And so it's zero-dimensional. Its degree is the degree of f1, fs, the number of zeros. It is still radical, everything is fine. And the shape lemma for this one is almost the same as the shape lemma for this one. Because the linear form that we chose for the shape lemma, which separated the zeros of f1, fs, the zeta, also separates the zeros of this one. So we can choose actually the same linear form for the shape lemma here. This implies that omega 0 is the same, omega 1 up to omega n are the same, and the only one left is omega n plus 1. I only have one more polynomial because I have one more variable, which is the image, no, x n plus 1 is sent to omega n plus 1 divided by omega 0 prime. This is a shape lemma. And what happens is that under this, we know the size of this, of omega n plus 1, because we did it with a shape lemma. But what happens is that because of the definition of this ideal, we can show that something that I forgot. Where is it? We can show that, okay, u of x, of p of x, of p, u of p, under this map equals omega n plus 1. And this is very easy to show because xn plus 1 equals p of x mod j. Xn plus 1 equals p of x mod j. See that? And then it's easy to derive that when I put u in this map, u of p is equal to omega n plus 1. And we have the bound size for omega n plus 1. A bound for the size of omega n plus 1. Then we have a bound for u of p. And once we have a bound for u of p, and what did we want? We didn't want a bound for u of p. We wanted a bound for this one, for the remainder of p. But u of p and u of the remainder of p are the same. So using the uniqueness of writing p bar in the quotient ring or in the basis, using that there is a unique expression here, I can use u of p, which is also, a little bit less, I still, here. Sorry for, I'm going maybe too fast. So I'm looking for this p. I'm looking for this p. But I know that u of p is equal to u of p bar, because p minus p bar belongs to I. So I know that they are equal. But this is equal to the sum of u of b. And I need these coefficients. So now look at the system I have. So the only thing is that I know the size of this guy because I just computed it, the size of u of p. I know the size of these guys because the base is b, I can compute that. So I know everything, the only thing I need is to know who is this one. This is a linear system of equations that I can solve. And the size of this linear system of equations is capital D. And this is how we derive the bounds here for the numerator and the denominator in the remainder. So this is I think it's one useful consequence of the shape lemma, that we can compute short description of the remainder, mod I. Good that I'm changing subject. So anybody who is completely lost can try to get in. Okay? If I move on? I think I'm going back to the Nullstellensatz. Let me see. C'est quand il veut. Hein? Ah, mais attends, j'ai ici. Here. I'm going back to the Nullstellensatz. Oh my God, it's wrong. No, okay. The only mistake I'm seeing is that it says G1, G2, and it shouldn't say G1, G2. It should say G1, Gn plus 1. So, can I erase all this? Or merci. Je perds toujours mon truc. Let me describe a little bit the proof by Jelonek, because this is the last, the most recent proof for the effective Nullstellensatz, and it's really beautiful because Jelonek, somebody mentioned him yesterday already here. So Jelonek found a kind of natural proof. So the input is that you know that I took n plus 1 polynomials because this is a generic case. So normally, when you have n plus 1 polynomial, if you decrease the dimension every time you add one polynomial, after n plus 1 polynomials, you will get an empty variety. So this is a generic case, but the proof is true. The same proof holds for any S polynomials bounded by n plus 1 polynomials. And if you have more than n plus 1 polynomials, you usually perform linear combinations of the polynomials to get n plus 1 polynomials. So I'm doing it in this case for simplicity. So where it says G1, G2, it should say G1, Gn plus 1. So the situation is that you have n plus 1 polynomials in C of x such that the variety is empty, which means that you can write 1 as a polynomial combination. And you know there is a polynomial combination, but you don't know the GIs. And you want to find GIs. So what the guy did, he defined the following morphism of algebras, which is the x from C of x, Z1, Zn plus 1. So this is a polynomial ring in 2n plus 1 variables to the polynomial ring in n plus 1 variable. So we have Z1, Zn plus 1, and then here Z is a single variable. It's not a bold Z, it's a normal Z. So 2n plus 1 here, n plus 1 there, and the morphism is that, okay, the variables xi go to xi, no change, but the variable zj go to z times fjx. And what happens is that this morphism, it's an algebra morphism which is defined on the variables. I'm doing something wrong here. And what happens is, look what happens in your unknown polynomial combination G1, Z1 plus Gn plus 1, Zn plus 1. When I do that, it's G1 of x doesn't change, and this is changed to Zf1 plus Gn plus 1, Zfn plus 1. But you know that G1 f1 plus Gn plus 1 fn plus 1 is equal 1. So it gives Z. So this is an epimorphism, right? So this, and the kernel of this epimorphism is an ideal here, a polynomial ideal here, which makes that R divided by I, let me see if I continue it here. Where is it? Oh, okay, it's an epimorphism, which gives this isomorphism here, okay? So the dimension of this quotient ring is exactly n plus 1. Here we have an isomorphism. Dimension, when I say the Krull dimension, the number of the transcendental degree here. So this has n plus 1 free independent variables. So the dimension of this is also n plus 1, okay? So there are n plus 1 free variables hidden here. So let me continue. I will simplify a little bit I will make a simplifying assumption, but it's without loss of generality. So here you have exactly n plus 1 free variables, and the other variables are algebraic over these variables. So imagine that your free variables here were z1 to zn plus 1. It's not always the case, but I will explain how this is not a loss of generality. So imagine that z1, zn plus 1 are the free variables in this quotient ring, which give the dimension, which give the Krull dimension. Which means that every other element here, and imagine something more. Imagine something more, that that my quotient ring is integral over C of z1, zn plus 1. So imagine that this happens. What does that mean, that it's integral? That not only all elements in this quotient ring satisfies an algebraic dependence equation over this mod I, so in this quotient ring satisfy an algebraic dependence equation over this, but the algebraic dependence equation is monic. So the polynomial, which is satisfied by any element here, starts with a 1, and then t to the d plus other terms. So imagine that this happens. That means that for any element here, there exists a polynomial in z1, zn plus 1, t, which is monic in t, such that for any element here, this element satisfies, if I plug it here instead of t, it satisfies that this is 0 mod I. Okay? So I forgot to put who is this element here. So every element in this quotient ring satisfies an equation like this in the quotient ring. So I will apply this. Sí, perdón.
For each p? For each element?
Actually, it's for each element, but I will apply this dependence for the element. I will choose, okay, for t equal g1 x z1 plus gn plus 1 x zn plus 1. This is one element here, and I will this element, since it belongs here, satisfies an integral dependence equation. So here is my integral dependence equation. And if I plug, instead of t, I plug this element, this will be 0 in the quotient. So it will be 0 mod the kernel. Okay? T is equal now to this element. Okay, so let's look at that.
So the fact that the polynomial has a capital D, which is
No, it's not exactly. No, in the notes I put nothing to do with the other D. It's because I didn't have another letter. I didn't know which letter to choose. So it's kind of strange. I don't know if degrees of polynomials is D or D or that's, sorry. Yeah, it's not the same D. So when I put here this element, this gives 0. So when I apply, because I apply phi, it gives 0, right? Because it's in the kernel. So it's in the kernel, so when I apply phi, it gives zeros. But what is applying phi? Phi is the phi that I had before. So this is my element. What is phi of this element? I said that phi of this element was z. So which means that z to the d plus sum pg of, what is the image of z1, zn plus 1? The image is zf1, zfn plus 1, right? Times z to the d minus j equal 0, right? We have this expression. This is Jelinek. It's not me, Jelinek. We have this expression is equals 0. Look at the coefficient in this expression of z to the d. The coefficient of z to the d here is 1. The coefficient of z to the d in this expression equals 0, right? 1. And when you look here at the coefficient of z to the d, you have to take something here of degree j in z. But look, everything has f1, fn plus 1. So when you look at this, in this expression, you can take out 1 of f1 of n plus 1 in each of these terms. So the coefficient of z to the d will give the Bézout identity for f1, fn plus 1. This is a question of looking at it, writing this polynomial and see, because this polynomial is a polynomial in z, which will be z1 to the something plus zn plus 1 to something. So when you expand this, you will have in every term, you will have one fi that appears at least. And you put that fi in common factor, and you will have your Bézout expression. And that's Jelonek's proof. So the whole thing for Jelinek was to find this polynomial. So this polynomial, that is the implicit equation for the element t. So I cheated a little bit because I said that, okay, imagine that z1, zn are the variables such that every polynomial is, every element of my quotient ring is integral over c of z1, zn plus 1. That's not always the case, but using the famous Noether normalization lemma, we can perform a change of variables in the variables x, z, zeta, z. We can perform a change of variables such that we take linear combinations of x, z, n plus 1 linear combinations of x, z, x, z, z, like this. So we can take n plus 1, using Noether normalization lemma, we can perform a change of variables and choose n plus 1 linear combinations of x and z1, zn plus 1, such that my quotient ring is integral over C of L1 ln plus 1. So C of L1 ln plus 1. So this is not a normalization lemma. It's, for instance, it's explained in the Atiyah McDonald book as an exercise. And the good thing is that not a normalization lemma is an inductive process, very easy, and you can see when you do it that in fact this can be chosen as Z1 plus L, another L, linear form, another linear form. How can I call that? Lambda, thank you. Fx, lambda 1, this can be taken as Z1 plus lambda 1 of x, and this can be taken as Zn plus 1 plus lambda n plus 1 of x. So the linear forms, I have enough room for choosing the linear forms such that I can choose them this way. And when I choose them this way, it doesn't change anything in the reasoning. So that is what Jelinek did. He did more generally, of course. He did it over varieties, but this is the essence of the idea of his proof. And what is very beautiful is that he found the right map, the right polynomial map. So I don't know if I convinced. So we didn't finish yet. So that is the next subject. So the whole thing is computing this P. These ones are polynomials on the FIs? No.
When you look at the coefficient.
Not all. You can have maybe only one FI1, and if you take it in factor, the GI will have nothing to do with the FI. Here you have an expression with lots of these FIs, but part of this expression will only have one F1 or one Fn plus 1. If you take degree, I don't know which degree here, you have to look at that. But it doesn't mean that the GIs are expressions of the FIs, no. No, you have to take them into factor. Tu en prends un? Ouais, sorry.
This is because the p's depend on the polynomial p will depend on the FIs, no?
Polynomial P will depend on the FIs.
Yeah, structurally it will change if you change the FIs.
Yes.
This is why it's...
No. I don't think it.
If p is independent, then what Bernard says, you expand and you will always get the polynomial expression of one friend.
I don't understand the point, sorry. Bernard, are you convinced? Not yet. Okay. Now, yes? Because I can explain it later. Sorry. So that was kind of to introduce, presenting a little bit this Jelinek's proof that I find beautiful, is to convince you about the next and last subject of this, which is Perron theorem. Perron theorem. So this is something very much related. It's not exactly the same. So Perron book, I think I will finish early. Is that a problem?
No. It's up to you.
Yeah.
You offer a longer break to the participants.
And to me too. So anyway, Perron theorem is Perron, I don't know how to pronounce it, he's a German mathematician, and he wrote a very famous book on algebraic geometry in the mid-90s, I guess. And it was very, very successful. And when he brought that book, it seems that it was gone immediately. Everybody bought that book because it was very nice to learn basic algebraic geometry. And one observation is that, so in the general setting, if you have in a polynomial ring with n variables, if you have n plus 1 polynomials, n plus 1 polynomials in n variable cannot be algebraically independent. Because if n plus 1 polynomials were algebraically independent, you would have a degree of freedom of n plus 1. But if you have a polynomial bringing n variables, you only have n free variables, right? That is a transcendental degree. Agree with that? N plus 1 polynomials in n variables cannot be algebraically independent. So there is a polynomial dependence equation. And I can use the last blackboard. For instance, if you have f1, fn plus 1 in k of x1, xn, there exists a polynomial p in the variables, let's say, a1, an plus 1 in k of a1, an plus y1, yn plus 1, non-zero polynomial, such that p of f1, fn plus 1 equals 0, right? Because of this question of free variables. And for instance, very easy, if you take f1 equal x1, fn equal xn, and fn plus 1, any polynomial, the algebraic dependence equation is very easy because it's in plus 1 minus fn plus 1 of I. This is the equation you would have. Sorry that I'm... If you plug, instead of in plus 1, you plug fn plus 1 minus fn plus 1 of x1, xn, it gives 0. So that is the simplest case, let's say. But what Perron did in his book, he gave a degree bound for the degrees in x1, xn of this polynomial p. He gave a proof, a combinatorial proof of the degree of this polynomial p. And it's very, very, very sharp in the sense that the degree he shows is that if, here, and it is a combinatorial proof. It's based on the pigeonhole principle. It's based on if you have so many variables and you solve a system, then there will always be a solution because you have, I don't know, less equations than unknowns and this kind of stuff. So what his bound is, I have it, Perron, is that if P is the sum of C alpha y1 to the alpha 1, yn plus 1 to the alpha n plus 1 is the algebraic dependence equation for f1, fn plus 1, then, and f1, fn plus 1 have degree d1, dn plus 1, then the bound is that alpha 1 d1, here is where we are going to plug f1. So f1 to the alpha 1 has this degree, plus alpha n plus 1 dn plus 1 is bounded by the product d1 dn plus 1. This is Perron theorem for this algebraic dependence equation. So finding this algebraic dependence equation for n plus 1 polynomial is very much related to the problem we had before of finding the polynomial p which is not written here. The polynomial p that we were looking in the last. Okay, it's very much related, actually. Before I had n and n plus 1 and n plus 1. And here I have n plus 1 and n. But the fact is that since z is integral, you can just invert it, and you can consider it as a parameter instead of considering as a variable. So doing that, we end up in the situation that we have n plus 1 polynomials in a polynomial ring of n variables. And then we can apply an arithmetic Perron theorem. Here I simplified it. I simplified the statement because the statement looked like that, and also looked like that for the height of P. So we can find an integer polynomial dependence equation for f1 fn plus 1, which satisfies some height bound. It's more precise than what is written there, but it looks ugly, so I just decided to simplify everything and to take degree bound for the max of the degree of the fj's and the h bound and height bound for the max of the h of the fj, just to show that it is simpler. And this is a crucial argument in our proof of the arithmetic Nullstellensatz, because this is when we, with Martin Sombra and Carlos de Andrea, we proved the arithmetic Nullstellensatz that I showed yesterday. What we did actually is make J-X proof arithmetic. So we added all the arithmetic bounds in J-X proof. And this was a crucial step in that proof. So this is, I think that it's enough material for a Friday morning after bouillabaisse. But before ending, I would like to take profit of the fact that I am the last speaker of all speakers, to really thank the organizers for this incredible event and for all the work they have done. So thank you very much, and see you next year, right? That's